Okay, so we are in Generalized Linear Models with examples in R, that book right there. And we are on, where are we? We are on question 2.11. Okay, so this is a three-parter. It starts off a little bit confusing because it gives us a model that was previously discussed, and then it uses some similar kind of funky looking terms to ask us to discuss a slightly different thing, but that's okay. So you can read this if you want, but I'm just going to jump to part one. So in part one, we are meant to use a Taylor series expansion of log of y about mu, where mu is the expected value of y. Okay. So now in the previous question, question 2.10, so you can go back and look at that if you want, but we looked at how to do Taylor series expansions, and so that's what, so I'm just going to plug and chug here. When I give my answers, so I'm giving answers obviously in the natural log, which is what this book is assuming, but just to make that explicit, I will usually use ln instead of log. So anyway, so our Taylor series expansion around the expected value of y being mu would look more or less like this, okay, this top line, right, where our function of y here is the natural log, right? And so, well, our function of y is the natural log of y, okay? So, so just going through, I'm just going to, put the natural log in everywhere. So I have the natural log of mu instead of f of mu. And then I have the first derivative at mu, okay, which is 1 over mu, right? So that the derivative of the natural log is 1 over whatever you're taking the derivative of, and so on and so forth. Okay, so if some of these other terms don't quite make sense, again, check out the video I did previously, or maybe even better, check out the Khan Academy lessons on Taylor series. Okay, and there's a link up above there. Okay, so anyway, so there's our Taylor series expansion for part one. And now, in part two here, we're meant to take the expected value of both sides of this equation, both sides being natural log of y and then the other side being this right here, and show that the expected value of the log of y, is approximately equal to, well, the log of mu, or the log of the expected value of y. Okay, so notice that it is approximate. Okay, it is not completely equal, but so let's just kind of start plugging through this. So we have the expected value of the natural log of y, right? That's this part right here. Okay, and then I'm just going to take the expectation of each term in my Taylor polynomial. Okay, I could take the expectation of the whole thing and then break it out into the individual expectations, but I'm just kind of skipping a step a little bit. So I have the expectation of the natural log of mu plus the expectation of 1 over mu dot 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 dot. Okay, so you can kind of see that for yourself there. Now, mu and the log of mu are both constants, and the expectation of a constant is just the constant, okay? So we can rewrite that as, so I can get rid of that expectation because the expectation of the log of mu is equal to the log of mu, okay? And similarly, the expectation of this guy right here can just come outside, well, of this guy, and this guy can come outside of the expectations. And so now I have all of this. Okay. So we can continue to simplify this. So here the expectation of y minus mu is 0, right? I mean, that's really the definition of mu. Okay. And then the expectation of y minus mu squared, well, that's actually the variance. Okay. So this is actually just the variance of y. Right? So after all of that, so this term drops out. This becomes the variance of y, and so this could be simplified to this guy right here. The expected value of the natural log of y is equal to the natural log of y minus 1 over, well, you can read it for yourself, plus infinite more terms. Okay. Now we are supposed to show that this guy approximately equals this guy. Well, that's what we've done here, right? So we have that it equals this, or that the expectation of the natural log of y is this, with many other terms here. But in other words, the natural log of y is an approximation for the expectation of the log of y. Okay, and so that's what we get. And this is what we were meant to show in the first place. Okay. Okay, so now using the information that we have discovered, I guess, so far, show that an increase in the value of x by 1 unit is associated approximately with a change in mu, which again is well, it doesn't matter, a change in mu by a factor of e to the beta 1. Okay. Okay, so let's kind of get going through here. Okay, so given that the expectation of the natural log of y is equal to, or I should say approximately equal to, I'm going to change that actually. Okay, so the expectation of the natural log of y is approximately equal to the natural log of mu, and that is approximately equal to our linear model here, beta naught plus beta 1x. Okay, well, now in this format then, let's just look at this. Here, a 1 unit increase in x causes a beta 1 change in the natural log of mu. That's a true statement. Okay, but we don't want to know what happens to the log of mu. We want to know what happens to mu. Okay, so what we need to do is we need to inverse the natural log here. And so we do that by exponentiating the natural log. Okay, but when we exponentiate one side, we have to exponentiate the other side. And so we come out with, so we've exponentiated the log of mu, which just gives us mu. And that equals, so now I'm exponentiating the other side. And I can rewrite e to the whatever, when I have a sum here, I can rewrite that as the product of the terms there. Okay? Good. So what this means is, now a 1 unit increase causes a change to mu, but it does it multiplicatively, not additively. Okay, so now a 1 unit increase in x multiplicatively increases mu by a factor of e to the beta 1. All right. Now you know if you're really familiar with this, with exponents and stuff like that, that might be intuitively obvious, but let's just use an example. So let's take that mu naught equals mu when x equals 2, right? So we'll just have x equals 2 here. Okay. So mu naught looks like this, okay, where 2 is my x. And then mu 1 will be mu when x equals 3. So it looks like this. Okay. Well then, if I want to know how much bigger mu 1 is than mu naught, then I can just set them as a fraction. Okay. Now my e to the beta naughts cancel out, and then I'm left with e to the 3 beta 1 over e to the 2 beta 1. So all that we're left with is e to the beta 1. So again, what that means is, by increasing x by a unit of 1, I am increasing mu by a multiplicative factor of e to the beta 1, and that's what we were meant to show. Okay.